Hello, what's up, guys? How are you doing? We're gonna learn about Kirchoff's law. We begin with Kirchoff's current law. So, states that the algebraic sum of currents entering a node is zero, just the summation of the currents entering and leaving. So, passing through the node is the summation is zero. Simply explained us the sum of the currents entering the node is equal to the sum of the currents leaving the node. For example, if we have such like different branches, like here also some kind of resistor. So if this is I1, this is I2, this is I3, the current in the branch, I3 the current in this branch, I2 the current in this one, I1 the current in this branch. So the summation of currents entering this node lets the current in this branch entering and divided between two. So Kirchhoff's current law states that the current entering I1 plus I2 plus I3 is equal to 0, or the summation of their summation is 0. So as you see, this one is entering the node and this two is leaving the node. So conventionally we can say that dose of currents entering the node can be depicted as the positive one, and dose of the currents entering leaving the node can be depicted as negative I2 minus I3, which is equal to 0. So in order to help us to solve problems or analyze a situation of a circuit, so I1 can be I2 plus I3. So maybe the multiple branches, just multiple branches like this. So as you see, this is the node. These three branches are entering the node and these two are leaving the node. So I1 plus I2 plus I3 is equal to I4 plus I5. So I4 and I5 are leaving the node. First it were like this: I1 plus I2 plus I3 minus I4 minus I5, which is equal to 0. Their summation must be 0. So in order to analyze this situation or calculate, we can move these two branches in the other side. So we can take those of branches, those of the currents, those of the currents on the branch leaving the node can be depicted as negative, and those of entering the node are positive, or vice versa. It's possible. So this law also works for a closed loop, like a closed loop like this one. A closed loop like this one. This closed loop can be considered as a node. So their summation, just so the current entering these two node, so the current on these three parts x, y, z, so their summation can be 0. Kirchhoff's current law can help us combining current sources which are held in parallel. So guys, one of the application of KCL is combining current sources which are held in parallel, which have the same node. So current sources which are on the same direction can be added, and those which are in opposite direction is subtracted from the whole, as you see. So IR is equal to I1 plus I3 minus I2, because I2 is heading to the opposite direction of the other plus I4. Like this circuit can be reduced into this form, as you see, can be reduced in this form. So if there is more current sources or like more branches which are in parallel, so these four circuits, these four branches are sources are in parallel, as you see, because they share the same two node. So their combined current is, their summation of the current is 0 according to KCL. This is one of the application of KCL. So IR is equal to I1 minus I2, because I2 is heading to the opposite direction, plus I3 plus I4. So can be combined into new IAB or IR. IR and IAB is the same because they are now in series. The other is the Kirchoff's voltage law. States that the algebraic sum of all voltages around a closed path or a loop is 0. For example, we can say this one V1, V2, V3, V4. So this is the closed loop. So KVL states that the summation of voltage from V is equal to, from M is equal to, M is the number of branches, to up to N is 0. So this means V1 plus V2 plus V3 plus V4, the closed path is this one. This also another closed path. This also another closed path. So V1 plus V2 plus V3 plus V4 is equal to 0. We're gonna solve more practical problems, and this is just to to explain how it works. So we're gonna solve some practical problems. This is also another example. If you see right here, we have V1, V2, V3, some kind of source, another element. So KVL status minus, as you see, this is the direction. So this shows the direction of the current flows in the loop. So in the loop, this is like a specific loop from this is one of the loops from these multiple loops, just taking one of the loops. So as you see, V1 is a source, this is V2 is some kind of element, a voltage across some a resistor, a voltage across a resistor. V3 is another voltage across a resistor. V4 we have here a source. V5 is another element, so a voltage across another element. So KVL states that the summation of voltages around the loop is 0. So V1, conventionally, as we have learned before, current entering to the negative terminal, passing through the positive terminal, or leaving through the positive terminal, the voltage is negative. The voltage is negative. This convention, entering to the positive to the negative, then it's positive. Positive for this one, negative for this one, because it enters into the negative terminal, and positive for this one, V5 positive, V1 and V2 voltage sources. In this elements, energy is dissipated. Simply, this convention help us to calculate and analyze situations. So rearranging the terms, V2 plus V3 plus V5 is equal to V1 plus V4, which means sum of the voltage drops on the element is equal to sum of the voltage drops is equal to the summation of voltage rises. So when voltage sources are connected in series, KVL can be applied to the total voltage. As you see, when voltage sources are connected in series, they can be summed or they can be combined, added into VAB. The voltage across AB can be the sum of these three. So VAB is equal to V1 plus V2 plus V1 plus V2 plus minus V3 because the polarity is changed. The same polarities are added, different polarities are subtracted. This helps when we solve problems for voltage sources, current sources. Current sources are added when they are in parallel, and voltage sources are added when they are in series. So VAB is the combination or the summation of these voltage sources can be reduced into one VAB source, and IR can be reduced into the current IR into this one, So when they are in parallel, current source, this when they are in series for voltage sources. Now we can solve practical problems in the next session. See you.